All right, well, it's 8 o'clock, so I guess we can get started. So, everybody ready for an exam? We got an exam this week. I pushed it back till Thursday because of the weather last Thursday stopped us from having class, and I wanted to get in a review before we have the actual exam. So today is review, where this exam is going to cover chapters 3.1 through 3.4. So the whole point of today's class is to get everybody reviewed up and ready for the exam on Thursday. So I guess the best place to start is to ask if there's any questions from any of the homework. Okay. Well, then let's start at the beginning. What did we start off chapter 3 talking about? Functions and inverse functions. So let's start by making a table. And if we make a table, what does that tell you about the table? If we're making a table during a review for an exam, what does that tell you? That you might want to know this table when you get ready to take the exam. So let's look at our functions. Yeah, you know what? I'm going to put them in a different order. Here's a tidbit for you. We haven't really discussed it, but just in terms of vernacular, have any of you ever seen the expression arc sine or arc cosine or arc tangent? You'd have seen something like arc sine theta. This is just another way of saying the inverse sine of theta. Okay, the arc functions are the inverse functions. It's just a different name for the same thing. So, I'm not going to throw that at you on the exam, but if you find yourself reading an engineering book or a nursing book and they talk about the arc sine of something or the arc tangent, that's what they're talking about, the inverse function. All right. Now we've got our table all set up and ready to fill it in. So let's start with asking the first question, what is a function? And for everybody who's just coming in, make sure you get a hold of the sign-in sheet and everybody gets signed in. That you have it? Has anyone not signed in yet? Okay. Make sure you sign it before you leave. So, now who wants to tell me what is a function? Not necessarily a trig function, just any mathematical function. No volunteers? A say again? Travis knows? Fine. Okay, Travis. Enlighten us. Nope. No, not even close.
What's a function?
What's on third? What is a function? No. A function is a set of ordered pairs. It might be a finite function. It might be an infinite function. The set could be finite or it could be infinite. That is a function. That is one, or it is a set of an ordered pair. An ordered pair is a set of coordinates, a set of numbers, an x and a y. Hence the word ordered. The order matters. That's one type of function. Another type of function would be an infinite function. A function of x equals x squared, or y equals x squared. So for every x you plug in it, it gives you a value of y. You can tell if a function is a function if you look at it graphed out on a chart. If you can draw a vertical line that touches that graph in two places, anywhere, it's not a function, at least not at that point. Now, in some restricted domain, it might still be a function. You can take out a piece of that graph where it passes the vertical line test, and that part of it is a function. But in order for it to be a function, there cannot be anywhere that you can draw a vertical line that will touch the graph in two places or more. That is, basically, that's a function. Now, what is an inverse function? That's the condition for an inverse function. Let's see if I can write this correctly. Y of x is the inverse of f of x if for every x that you plug into f of x gives you, I guess I should write this, you know what? I'm afraid I'm about to just confuse everybody with a lot of unnecessary, because this is, let's just forget about that. We're not going to worry about that definition, okay? But an inverse function is a function that gives you the original value that you plugged into the function. Okay? The easiest way to visualize a function without worrying about all the mathematical definitions is that the inverse of a function is what you get if you take the graph of the original function and mirror it along this line of y equals x. So if this is your original function, then your inverse function would look like this. Okay? Now, if it is an inverse function, it must be a function. Okay? So, now because it's inverse, the domain of the original function the domain of f of x must be the range of the inverse function of x. And the range of f of x must be the domain of the inverse of f of x. So you start with the domain and range of your function, and they have to be swapped for the inverse function. It's simple as that. The domain of the function is the range of the inverse function. And the range of the function is the domain of the inverse function. So now we get to what is the condition that must be true in order for a function f of x to have an inverse function. Anybody, shout it out. Go ahead. You said it a while ago.
1 to 1.
It has to be 1 to 1. Very, I mean, you're all familiar at least with the trigonometric functions right now. Not a single one of them is 1 to 1. They are all periodic. I mean, that's kind of by definition. They go around a circle. And that means that for every value of x, you are going to get an infinite number of y's. Okay? I'm sorry, I got that backwards. For every value of y that you get out of sine theta, there will be an infinite number of x's. There can only be one value of y for every value of x. That has to be for it to be a function. But that doesn't mean there's only one value of x that will give you that value of y. And in the case of all of these trigonometric functions, pick any value of y in their range, and you will get an infinite number of x's that produce that result, that produce that y. That means that sine, cosine, tangent, none of these trigonometric functions as they exist can have inverse functions. They have to be 1 to 1. So, in order to have an inverse function for these trig functions, we have to restrict the domain of the original function. So, let's start with sine of theta. At 0, it's equal to 0. At pi over 2, it's equal to 1. At pi, it's back to 0. At 3 pi over 2, it's down to a negative 1. And at 2 pi, it's back to 0. Where is this 1 to 1? Well, we could define it from here between pi over 2 and 3 pi over 2, but in fact, the way it's generally defined is between minus pi over 2 and pi over 2. As a general rule, you want the origin in every function and every inverse function. So this is what's called the fundamental period, or the fundamental half period of sine. It's in this range, in this domain from minus pi over 2 to pi over 2, sine of theta is a one-to-one function, and so this is where the inverse sine is defined. So let's start filling out our table. What is the domain of sine theta? No, that's the restricted domain for the inverse functions, for purpose of the inverse function. But for the sine function of theta, what is the domain? Where is, what values of x can you plug into sine theta to get a legitimate, a unique answer, a value of y? Negative infinity to infinity. Using the curved bracket, the curved parentheses, because it's non-inclusive. You can never get to infinity, positive or negative. The curved brackets mean, the parentheses means that this is negative infinity to infinity, not inclusive of the endpoints. Now, what is the range of the sine function? Negative 1 to 1, one more word, inclusive. So we use square brackets to signify that it's inclusive. Minus infinity to plus infinity, non-inclusive is the domain of sine. Negative 1 to 1 is the range of sine. Pi over 2. This is the restricted domain of the sine function for the purposes of generating an inverse sine function. If we did an inverse of the whole thing, then it would not be a function. Because wherever you plugged in, whatever value of x you plug in, you would get an infinite number of y solutions. And so to make this, to define an inverse function, we have to have a restricted domain where the sine function is, what's the one condition? In that domain, the sine function is 1 to 1. It also gives you every possible value in the whole range of the sine function. That's important. Now, what that means is when we start talking about the domain of the inverse sine function and the range of the inverse sine function. Okay? What's the domain of the inverse sine function? And before you answer, even though we've just been talking about the restricted domain of the original sine function, remember, when you go to an inverse, the domain and range have to swap. The domain, exactly. The domain of the inverse sine function is minus 1 to 1 inclusive. What does that tell you? If you're working on solving a trigonometric equation, then you're trying to find solutions, and you get down to something like the inverse sine of theta equals minus 1.7. What would that tell you? Thank you. No solution. Minus 1.7 is not in the domain of the inverse sine function. So you cannot plug it in you can't plug it in. That's saying, what this is saying is that if you take the sine let me think this through, because I think I don't want to confuse you. The inverse sine of theta is minus 1.7 would mean that theta is equal to the sine of minus 1.7, and that is perfectly acceptable. It would, but it would it would give you a result, but it would be outside the original domain, outside the restricted domain. No, telling you, you got to wrap your head around this stuff. The inverse sine of theta being 1.7, what you're saying is the sine of theta is 1.7. The sine of theta is 1.7. That cannot happen. So the inverse sine of the sine of theta equals the inverse sine of 1.7. And that cannot happen. Okay? Why is this? Because there is no angle theta that will give you a sine of 1.7. Right? Prove it to yourselves. Get out your calculators. Plug in 1.7 and take the inverse sine. It's going to tell you error. Okay? This is why. Because there is no value of theta that the sine of theta will be 1.7. Everybody, help me recite this, because this is important for you to remember. When you take the inverse sine of a number, what is the result? The inverse sine of a number is an angle whose sine will give you that number. Right? If you take the sine of an angle, you get a number, a coordinate on the Cartesian coordinate plane, the y-coordinate to be specific. So the sine of an angle is a number. That means the inverse sine of that number is the angle that will give you, that the sine of which will give you that original number. Okay? And since there is no angle that will give you a number greater than or equal to greater than 1 or less than negative 1, there is no number greater than 1 or less than negative 1 that you can legitimately plug into the inverse sine function. Everybody understand this so far? Now what does that give us? What is the range for the inverse sine function? Nope. Now we've got to go back. Remember, the range of the inverse function is the domain of the original function. Now we come to this restricted domain of the original function becomes the domain of the original function. And it is minus pi over 2 to pi over 2, inclusive. The original function has values that's 1 and negative 1 at pi over 2 and minus pi over 2, respectively. This is right here. This is where that restricted domain comes into play. Now, you can plug in any value of theta, any angle from minus infinity to infinity, and ask for the inverse sine of that angle. But it's going to map you right back to this original domain of the inverse function of minus pi over 2 to pi over 2. Okay? Give you an example. Somebody get out your calculator and take the sine of 150 degrees. Got a half. Take the inverse sine of the half. And does it give you back 150 degrees? Gives you back, what, 30? Which, if you subtract that from 180, would give you 150. Yeah. Right. What you're doing is, here's your unit circle. Here's I don't know, what was it, 30 degrees? Here is, 60, however far here's 60 degrees. Okay, so you take the sine of 60 degrees and then take the inverse sine of 60 degrees. It's going to map you, I'm sorry, not the inverse sine of 60 degrees. You take the sine of 60 degrees, gives you, what, a half, was it? I don't remember the unit circle. The sine of 150, yeah. That's what I'm doing wrong. I wrote 30 and I drew 60. Try this again. Here's 30 degrees. Here's 150 degrees. You take the sine of 150 degrees, it gives you 1/2. But if you then take the inverse sine of that 1/2, it's not going to give you 150. It's going to bring you back to this minus pi over 2 to pi over 2 restricted domain. The range of the inverse sine function. In other words, every time you take the inverse sine of something, it's going to give you back the answer out of these two quadrants. From minus pi over 2 to pi over 2. Suppose you get minus pi over 4 as your answer. You take the inverse sine of what is that? Square root of 2 over 2? Minus square root of 2 over 2. You take the inverse sine of it and it gives you minus pi over 4. strictly speaking, if you wrote 7 pi over 4, that would be, it wouldn't be wrong, but technically speaking, it's not really correct because 7 pi over 4 is not, it's equal to minus pi over 4. But it isn't actually the same because this is minus pi over 4. This is 7 pi over 4. Okay? Of course, that's a little bit esoteric. So if your calculator, whatever your calculator gives you, it gives you minus pi over 4, or it gives you 7 pi over 4. It's not going to give you 7 pi over 4, but if you do the math in your head and you come up with 7 pi over 4 instead of minus pi over 4, I'm not going to count that wrong, but I just want you to understand, strictly speaking, it's not exactly correct. It's just equal. Okay? But everything equal is not the same thing. Okay? 1/2 is equal to 2/4, but they're not the same fraction. They're two different fractions. They're just equal. All right, let's finish filling out this table. What's the domain of cosine? Minus infinity to infinity. One more word. Exclusive. Use the curved, use the parentheses. What's the domain? What's the range of cosine? -1 to 1 inclusive. Very good. Okay, now then what is the domain of cosine? -1 to 1 inclusive. Now we need the range for cosine, but be careful. It's going to be 0 to pi. Because here is that primary interval, that primary domain of the original function that's 1 to 1. So the sine, inverse sine function gives you a range of minus pi over 2 to pi over 2, but the inverse cosine function gives you a range of 0 to pi inclusive. All right? Now, this one's going to get a little tricky. What is the domain of the tangent of theta? No, it's going to be restricted too, but for just the original tangent function, the domain is minus infinity to infinity, but with a caveat. It is undefined everywhere. What's the tangent? Is sine divided by cosine. So what happens when cosine is equal to 0? Tangent is undefined. That's where you start running into your asymptotes. We're going to look at the tangent function. Cosine is 0 at plus and minus 90 degrees, at pi over 2 and minus pi over 2. So at pi over 2 and minus pi over 2, tangent is undefined. That's where the asymptotes are. If you graph it out, looks like this. and this equals 1 and minus 1 at pi over 4 and minus pi over 4. And then that same graph just repeats over and over again. So, the domain of tangent theta is minus infinity to plus infinity, except at odd multiples of k pi over 2. You see why it's odd multiples? Because at even multiples, it would be 2 pi over 2, which is pi. Well, it's perfectly well defined at pi. But at odd multiples of k pi over 2, it's undefined. So the domain of tangent of theta is minus infinity to infinity exclusive, except at k pi over 2 where k is odd. All right? Now let's look at that restricted domain of the original tangent function. Or the principal domain, where the tangent function is now 1 to 1. Oh, we forgot to do the range. What's the range of the original tangent function? What values can you get for output? Negative infinity to infinity. One more word. Exclusive. Now, that's the domain and range. What is the domain of the inverse tangent function? Negative infinity to infinity exclusive. Why exclusive? Because you can never get to infinity. Okay? It has to be a finite number, so it has to be less than infinity, but it can be as arbitrarily close to infinity as you want to get. Are there any restrictions on this domain of the inverse tangent function? No, no restrictions. But what about on the range of the inverse tangent function? One more word? No. Exclusive. Negative pi over 2 to pi over 2. Exclusive. You can't get to pi over 2. If you do, you get to an undefined, that's let's try to go through these others as quickly as we can. I hope I've made the point of how you have to think your way through these to understand why the restrictions are there. Let's look at the cosecant. What is the definition of the cosecant? Cosecant is 1 over sine. So what's the domain of the cosecant function? Negative infinity to infinity, except because it's defined as 1 divided by sine theta. So anywhere sine theta is 0, it would be undefined. Well, where is sine theta 0? At pi, at 0, pi, 2 pi, 3 pi, 4 pi at all multiples of pi. So it is the domain of the cosecant function is minus infinity to infinity, except at any multiple of pi, where k times pi for k equals any integer. And what is the range of the cosecant function? This is one of those weird ones. Yeah, the easiest way to write it is the absolute value of y is greater than or equal to 1. Right? This is the sine function. This is the cosecant function. Okay? But look at here. Now we're going to use this same restricted domain of minus pi over 2 to pi over 2 for creating an inverse cosecant function. And look what's happening. Right here at 0, at x equals 0, or theta equals 0, cosecant is undefined. So, what is the domain of cosecant of the inverse cosecant theta? Exactly. Any value of x, the absolute value of which is greater than or equal to 1. That's the domain of the inverse cosecant function. And the range is going to be well, wait a minute. Is it exclusive? Nope. At pi over 2, its value is 1, or is minus 1. I'm sorry, at pi over 2, its value is 1. Minus pi over 2, its value is negative 1. So it is actually inclusive between pi over 2 and minus pi over 2, represented with the square brackets, but not when y is equal to 0. It has no value at theta equals 0. The cosecant function is undefined. That means the range of the inverse cosecant can never give you y equals 0. The inverse cosecant function can never give you a y equals 0 result. So if you run into a solution, if you're solving an equation and you find where you've got the inverse cosecant equals 0, that cannot be. Going now to the inverse secant function. Well, first the secant function is actually, this is actually 1 over sine. This is 1 over cosine. So what's the domain of the secant function? It's also minus infinity to infinity, but with what restriction? Anywhere that the cosine is equal to 0. Anytime cosine is 0, secant theta becomes undefined. And cosine is 0 at odd multiples of pi over 2. And what is the range? Again, the output of the secant function will always return something greater than or equal to the absolute value of which is greater than or equal to 1. It can be minus 1 or less. It can be plus 1 or greater. Now that gives us a domain for the inverse secant function of the absolute value of x equals greater than or equal to 1. Here's our secant function. It's the inverse, it's the reciprocal of, yeah, and I drew that in the wrong place. It's the reciprocal of the cosine function. So it's going to be undefined at pi over 2. That means its range is minus infinity to infinity, exclusive. No. Yeah, it is. Its range is going to be 0 to pi inclusive, except when y is equal to pi over 2. Now, our cotangent function is 1 over tangent, or cosine over sine. What's its domain? Negative infinity to infinity, except where? Except wherever sine is equal to 0, which is any multiple of pi. Any k times pi where k is an integer. And its output range, cotangent, gives you anything from negative infinity to infinity without exclusion. But it's negative infinity to infinity exclusive. That gives you an input domain for the inverse cotangent of minus infinity to infinity exclusive, and an output range. What is the restricted domain? Is going to be, yep, because you're now doing, everything shifted. So you're now at 0 to pi is your output range. Is that inclusive or exclusive? Remember, on your tangent, the output was exclusive because you could never get to the asymptote. So it's exclusive here as well. Are there any restrictions? Is there any point in that fundamental period where the cotangent is undefined? No. No restrictions on tangent, no restrictions on cotangent. Except that it's 0 to pi exclusive. Y'all will definitely want this tablet, this table, for the exam. Okay? I don't know how more subtle I could make a hint than to tell you, you want this table on your index card for your exam. Now, we've still got a little bit more to cover. That covers pretty much sections 3.1 and 3.2 with the functions and the inverse functions. But now, has everybody got all this written down? Everybody got their pictures taken? Yeah. Now let's look at doing some of those solving for some of these things. And those of you who were here, remember we got into, by we I mean I, got into some trouble doing a homework problem because I forgot a very simple fundamental principle about solving these equations when you have these, you're having to solve these trigonometric equations. And that is that for every trigonometric equation, there is a period. Okay? Some trigonometric functions have two solutions in every period. Sine and cosine, they're reciprocals. But tangent and cotangent are different. How are tangent and cotangent different? There will only be one, but because the period of tangent is simply pi, not 2 pi. The period of cotangent is pi, not 2 pi. Period of sine, period of cosine, cosecant, and secant are all 2 pi. Now, what does that mean? What does that mean? Why is this important for you to remember? When you solve an equation, you do an algebraic solution to a trigonometric equation, you're looking for all the solutions to that equation. You're going to find one or two solutions in that fundamental, in that first period, that first time around the circle, or that first time around the half circle for tangent and cotangent. Okay, here, unit circle. There's your angle. X and Y. Sine of theta equals Y, cosine equals X. Tangent is Y over X. Y'all remember all of that. But you get if you're looking for sine and cosine, you get a solution here and here for sine. For cosine, you get a solution here and here. Because this is where both the cosines are positive. Up top is where both of the sines are positive. So if the solution is, after you solve the equation, you end up with the sign is equal to a positive number, then you're going to get two solutions, here and here. If it's a tangent or a cotangent, you're only going to get one solution. And it's going to be between here and, between 0 and pi, or between minus pi over 2 and pi over 2. It's going to be out of the range of the inverse function. Now, if the question asks you to write all of the solutions, then you're going to end up with something like theta equals pi over 6 and, I don't know, 5 pi over 6. Okay? But if they want all the solutions, then you have to know, you've got two solutions, so you know that it's going to be it's either a sine or a cosine or a secant or a cosecant function that you solved to get this solution. So when you write the solution, if you're writing it for all solutions, you would write theta equals pi over 6. You'd write k pi over 6. I'm sorry, you would not write k pi over 6. You would write pi over 6 plus k times whatever the period of the function is. Now, if it's sine or cosine, secant or cosecant, it would be k times 2 pi. If it's the solution to a tangent function, or an inverse tangent function, then it would be pi over 6 plus k times pi, not 2 pi. In other words, you're adding multiples of the period. Okay, so what is that saying? That's saying that, yes, the first solution you get to is going to be pi over 6. But because the period of the function is pi, then you're going to get that same solution at pi plus pi over 6. And then at 2 pi plus pi over 6. And 3 pi plus pi over 6. And 4 pi plus pi over 6. But by the way, for k equals an integer can also be negative numbers. So it would be it'd be pi over 6 minus pi. Pi over 6 minus 2 pi. Pi over 6 minus 3 pi. All of these are going to be valid solutions to the equation if pi over 6 is the first solution. But when you're writing these when you're writing an expression for all the solutions, this is what you want to write. You want to write the solution plus the period the k times the period for any integer k. Now, in this case, where you have two solutions, because you have an original function that has a period of 2 pi, then you would write theta equals pi over 6 plus k times 2 pi, and theta equals 5 pi over 6 plus k times 2 pi, for k any integer. And now you have literally written an expression that describes every possible solution to that equation. Because k is an infinite number of integers, you have literally written out an expression of an infinite number of solutions. Let's talk about solving these trigonometric equations algebraically. In particular, I want to make sure everybody remembers this. If you have an equation of the form let's put in real numbers. What is the amplitude of this equation, of this function? 3 is the amplitude. What's the angular frequency? Omega. 2. And the offset? Now, trick question. Everybody pay attention. What is the period of this function?
Pi over 2.
It would be 2 pi over 2. It's the period of the sine function, 2 pi, divided by the angular frequency. If this were sine of x over 2, omega would be 1/2. And the period would be 2 pi divided by 1/2, or 4 pi. Now, let's see if we can find an example to work through just to kind of refresh y'all's memories on how you go about solving these things algebraically. Here's one. Three times the inverse sine of x equals pi. Solving this algebraically, you divide both sides by 3, you end up with the inverse sine of x is equal to pi over 3. What does that mean? That means x is an angle, the sine of which is pi over 3. Does everyone have their unit circle somewhere on their card? Where would we find the sine of x equaling, what x would give us a sine of pi over 3? 1/2. What we're saying is the sine of the inverse sine of x is equal to the sine of pi over 3. So x is equal to what, 1/2? Is that the only solution? That's right. This is an inverse sine function. This is a solution to an inverse sine. So there is no other x in the domain of the inverse sine that will give you that solution. So the complete solution set for this is 1/2. These are not just randomly squiggled lines, by the way. They are supposed to be curly braces. Does everyone remember? Sometimes you have to factor an expression before you can solve it. See if they give us a good example of doing that in here. Here's one on page 212, example 7. 2 times sine squared theta minus 3 sine theta plus 1 equals 0. How would you factor this? Yeah, I know, I hate factors too, but I hate factoring too, but you can quickly confirm the factoring by just multiplying it out. FOIL, first, inner, outer, last. So you got 2 sine theta times sine theta is 2 sine squared theta. Inner would be minus sine theta. Outer would be minus 2 sine theta. And then minus 1 times minus 1 is plus 1. And minus 2 sine theta minus 1 would be minus 3 sine theta. So we get our original equation back, and we know we factored it. If you wanted to, if you just can't figure out how to factor it and you just want to plow through with the biggest hammer you can find, you could certainly plug this into the quadratic formula that's written on the board over there that I've conveniently forgotten to erase. Okay? Just in case one of you needs it during an exam or something. You could plug these into the quadratic formula and get solutions. But if you can factor it, we now know that either, in order for this to equal 0, one or both of these factors must equal 0. So anytime either or both of these equals 0, then the whole equation becomes 0. So when is 2 sine theta minus 1 equal to 0? when 2 sine theta is equal to 1, add 1 to both sides, divide both sides by 2, sine theta is equal to 1/2. When is sine theta equal to 1/2?
Pi over 6.
Pi over 6. When else?
5 pi over 6.
5 pi over 6. Okay, when will this factor be? When will this factor be? Sine theta equals plus 1. When does that happen? Pi over 2 only. You're never going to get sine theta equals plus 1 anywhere else on the unit circle. Now, what if the question was, instead of solve this equation on the interval of minus pi of 0 to 2 pi, what if it was find every solution for this equation? You've got 3 solutions to this equation, and it's of a sine function which has a period of 2 pi. So your total solution set would be theta equals pi over 6 plus k times 2 pi. Theta equals 5 pi over 6 plus k times 2 pi. And theta equals pi over 2 plus k times 2 pi, for k equals an integer. And that would be the expression of every possible solution to that equation. I see some furrowed brows. Now would be the time to speak up. Now would be the time to ask me about what it is you think the guy sitting next to you doesn't quite get a grip on.
Sine theta minus 1 on the second part.
Right here?
Yes, sir. I can come up with pi over 2.
In order for this entire expression to equal 0, one of these two factors must equal 0. Both of them can. So that means that sine theta minus 1 must equal 0. Add 1 to both sides, and we get sine theta must equal plus 1. When is sine theta equal to plus 1? When theta is equal to pi over 2 only. It's one of those, it's the sine will equal plus 1 and minus 1 once and only once each on the period, on the full period. For any other value of theta, it's going to be 2 answers. There will be 2 values of theta that will give you the same value of sine. But at pi over 2 and minus pi over 2, you get one and one only solution. Okay, one more thing that I need you to be aware of, that you need to be ready for on this exam. One of my favorite subjects, identities. What is the difference between an identity and a conditional expression? Okay, I'm not going to try and make up an example right off the top of my head, but it's a conditional expression. This is a conditional expression. Okay? This is true if and only if theta is equal to one of these results, one of these solutions. Okay? That makes this, by definition, a conditional expression. And you have to find the values of theta that make it true. An identity would be an expression that is true for every value of theta or x or whatever it's a function of. Okay? So, sine squared theta plus cosine squared theta equals 1 is always true no matter what value of theta you plug into it. For any value of theta within its domain, this will always be true. That makes it an identity, not just a conditional expression. And this is called, what's the special name for that one? The Pythagorean identity. If you can remember that x squared plus y squared equals 1, or equals the radius, then you will always be able to reproduce this identity. Just remember from your unit circle that x and y coordinates are the sine and cosine values. But you will also need to be ready to show that an expression is an identity by reducing it and simplifying it. That means you're going to want to remember that tangent is equal to sine over cosine. Cosecant is 1 over sine. Secant is 1 over cosine. If you don't have those written on your index, you can remember cosecant does not start with an S, so it goes with sine. Secant does not start with a C, so it goes to cosine. Okay, the initial letters don't match. That's how you can keep those two straight. Cotangent is 1 over tangent, which means it is cosine over sine. As a general rule, the first thing you want to do when you're trying to establish an identity is, as a general rule, you want to work on the more complex side of the equation. It's probably going to be something complicated equals something simple. So the best approach is usually to try to take the complex and simplify it. That will guide you towards a solution. If you try to take the simple and complicate it, then you just have this infinite branching out of possible combinations and permutations that tends to do the opposite. It gives you, unlimited options. And especially when you're working on a time limit, that's generally not a good idea. So work from complex to simple, not the other way around. Simplify the expression algebraically if you can. But go ahead.
So there's different forms of how that can be written.
There is. And if you find that you can simplify an equation until you end up with something like sine squared is equal to 1 minus cosine squared, then that's easy to reduce to the Pythagorean. You just add cosine to both sides of the equation. Or add cosine squared to both sides of the equation. But after you've algebraically simplified it, if you can, And sometimes, even if you can't, a very good place to start is to rewrite everything in terms of sine and cosine. So if you see tangent, change it to sine over cosine. If you see cosecant, change it to 1 over sine. And simplify from there. First of all, has anyone done any of the homework or have any homework to turn in? Does anyone have any questions from the homework that you would like to look at and go over real quick while we got a few more minutes? Well, pick one that's not going to embarrass me, because remember, I'm flying without a net up here. Believe it or not, I have not memorized this book. So, when I start working on these problems, I'm working without a net. Off of page 224, you said? Number 25, cosine theta times tangent theta plus cotangent theta equals cosecant theta. Oh, wow, way to go. Way to pick one that's not going to embarrass me. Let's do this. Well, let's see if we can do this. Cosine theta times tangent theta plus cotangent theta equals cosecant theta. Okay, is there any way to algebraically simplify either side? Not really. They're pretty simple, straightforward right now, aren't they? In fact, we're probably going to end up multiplying through by cosine. But let's not. Let's just start by rewriting everything in terms of sine and cosine. This is 1 over sine theta, right? So this is cosine theta times sine theta over cosine theta plus 1 over sine theta. No, plus cosine theta over sine theta. Okay. Multiply through by cosine theta. This cancels here, so this is left with sine theta plus cosine squared theta over sine theta. Oh, I see a cosine squared. I like that, as long as it doesn't turn into a cosine cubed, in which case we're backing up. And that would have to then be equal to 1 over sine theta. So now let's multiply both sides of the equation by sine theta, and we end up with sine squared theta plus cosine squared theta, which canceled out with that bottom sine theta, would be equal to sine theta over sine theta equals 1. QED, quadrata demonstrata. QED, it's a mathematician for there.
Where do you get the sine squared?
I multiply both sides of this equation by sine theta. So this becomes sine theta over sine theta, which is 1. This becomes sine theta times sine theta is sine squared theta. Sine theta times cosine squared theta over sine theta leaves cosine squared theta because the signs cancel. Way to go picking one that didn't embarrass me. Who did? That was 25.
I have sine u, cosine squared.
From what page? Yes, class is over. Y'all can leave if you want. Make sure you signed the sign-in sheet before you go anywhere.